Chapter number 3, current electricity. See, we all are aware about the importance of electricity in our day-to-day life, right? How electricity is important. Now, related to this electricity, we have to carry out some study in this particular chapter. Chapter number 1 and chapter number 2, which we discussed, are known as static electricity. It implies that in those chapters, we discuss this thing when the charge is stationary or steady. At that time, how it exerts the force, what is the field of it in the surrounding of it, like that. So all these studies were carried out. But now, if charge is in motion, then it constitutes current. Now, that electric current, first we have to understand here. Okay. See, suppose we have any conductor as shown in this figure. Now, if we imagine any cross section of the conductor, and through this particular cross section, suppose in a given time t, total positive amount of charge flowing, that is Q plus, as well as total negative amount of charge flowing, that is Q minus, from left side to right side as shown in this figure. Then the net amount of charge flowing through this cross section in the given time interval t, that we can write Q, that is equal to Q plus minus Q minus. Now, this net amount of charge flowing through any cross section per unit time, that is called electric current. So we can write electric current I, that is equal to Q by T. So we can say electric current I, that is nothing but the net amount of charge flowing through any cross section of the conductor per unit time. So here the SI unit of current, that is ampere. And from this equation, we can write ampere, that is equal to coulomb per second. Clear to all of you? Now, if the rate of flow of charge, that is constant one, then steady current is constituted in the conductor. And for that, we can write this equation I, that is Q by T. But if the rate of flow of charge is not constant one, then in that particular case, we have to consider delta Q, the small amount of charge flowing through any cross section in a small time interval delta T. So if delta Q is the amount of charge flowing through any cross section in time interval delta T, then we can give the instantaneous current at that particular instant. That is equal to limit delta T tends to 0 delta Q by delta T. Or we can write that is dq by dt. So instantaneous current, that is the rate of flow of charge at that particular instant. So we can write the equation of current I at any time t, that is equal to dq by dt also. Now from this particular equation, you can calculate the amount of charge flowing through any cross section of the conductor in a given time interval when the conductor is carrying current I ampere. So From this one, we can write dq that is equal to I dt. Now, if we integrate on both the side, then integration of dq that is q. That is equal to integration I dt between the limits t1 to t2. So this particular equation will give you the amount of charge flowing through any cross section of the conductor in time interval t1 to t2. Clear to all of you? Now electric current in conductors. See, we discussed this thing when the charge flow through the any cross section of the conductor in given time interval, then the current is constituted. We know this thing. There are large number of free electrons in the conductors, in metals. And all these electrons are executing thermal motions. But the motion of the electrons, that is randomized one. So when random motion of electrons is there, and if any type of electric field is not present in the conductor, then if we think about any cross section of the conductor, then through this particular cross section, the net amount of charge flowing in a given time interval, that comes to zero. Because when the motion of the electrons, that is random motion, then in that particular case, if as per example, we take suppose n number of electrons are flowing through this cross section in given time t from right side to left side, then the same n number of electrons will flow from this cross section on left to right side. So when we calculate the net amount of charge flowing through the cross section, then it will come to zero. So the current will not be constituted in it. Now, if we want to constitute the current here, then there should be some net flow of charge through any cross section of the conductor. Clear to all of you up to this one? Now, suppose we give some electric field to the conductor. How? See here in text, one simple example is given to you. As you see in this second figure, suppose we take two non-conducting plates having area exactly equal to cross-sectional area of the conductor. Then on one plate, we deposit positive charge. On another plate, we deposit negative charge. It implies that we can say one plate is made positively charged, another plate is made negatively charged. Now, attach both these plates to the ends of the conductor as shown in the figure. Now, one end of the conductor, that is, we can say positively charged, because there the positively charged plate is attached, and another end of the conductor that we can say is negatively charged, because there negatively charged plate is attached. So inside the conductor, from positive to negative, the electric field will be developed. Now we know this thing. When any charge is in the electric field, then force acts on it. that is Q into E. So here electrons will experience the force in the opposite direction of electric field. So some net flow of electrons will start through any cross section of the conductor in the opposite direction of electric field. But when this electrons reaches to the positive plate, it will neutralize the positive charges. So when the plate is completely neutralized, then after the current becomes zero. So here momentarily for some time interval, the current will be constituted. Clear to all of you? Now, for small time interval here, the current is constituted. But suppose we want to produce the steady current, then what we have to do? Then we have to make the provision of constant electric field inside the conductor. And now for that, except attaching the charged disk, connect the battery or cell across two ends of the conductor. Okay, so here now steady electric field will be produced in this conductor. Now electrons will flow towards the positive terminal of the battery and negative terminal of the battery will release the electrons, and here the continuous flow of net charge through any cross section of the conductor will be obtained, and resultantly you will get the continuous current through the conductor rather than the current for a short time interval. Clear to all of you? Now Ohm's law. See here, keep one thing in your mind before discussing this Ohm's law. Ohm's law is not the universal law just like the law of gravitation or Coulomb's law. Ohm's law, that is just an experimental observation. Okay, and it is not necessary all the substances in all the conditions obeys Ohm's law. Now see, under definite physical condition means say constant temperature, the current flowing through conductor that directly proportional to the potential difference applied across ends of the conductor. That is the Ohm's law. So we can write, if potential difference applied across two ends of the conductor, that is V volt, and current flowing through the conductor, that is I ampere, then we can write V proportional to I. Or we can say V by I, that is constant. And that constant, that is called the resistance of the conductor. Resistance, that is the feature of the conductor due to which it opposes the motion of the charge through the conductor. Okay, now we can write R, that is equal to V by I. So the resistance of the conductor, that is the ratio of the potential difference applied across the conductor to the current flowing through it, and its unit, that is known as ohm on behalf of the name of scientist, and this one is the symbol of unit. ohm. And we can write here ohm, that is equal to volt per ampere. Ohm, that is equal to volt per ampere. Clear to all of you this Ohm's law? Then after, just remember this word reciprocal of the resistance, that is known as conductance. So when this one is the reciprocal of resistance, so its unit means the unit of conductance that we can write 1 upon ohm. That 1 upon ohm that we can write as ohm inverse. And that ohm inverse is written as MHO, mho. And it's a symbol that is as shown here, that is also opposite to this one. Clear? Now we have to discuss the dependence of the resistance on the dimensions of the conductor. How it depends on the dimensions of the conductor, that we have to discuss. Suppose as shown in the figure, we take one conductor having length equal to L and cross-sectional area that is equal to A. Now, suppose here across two ends of this particular conductor, the potential difference of V volt is applied. And due to that, the current flowing through this conductor, that is equal to I ampere, then we can write V, that is equal to IR as per Ohm's law, where R, that is the resistance of this conductor. So here we can write R, that is equal to V by I. Now, suppose we take this type of another conductor having length equal to 2L. The type of the material of the conductor, that is the same one. So length, that is 2L, or we can say take two conductors like this as shown in figure A and arrange them as shown in the figure B. So the resultant cross-sectional area of this combination, that is A itself, but the total length of the conductor, that is 2L. Now, if here same I amount of current that you want to pass through this particular combination, then across these two ends of the combination, you have to apply the potential difference of 2 volt. Or here, experimentally, you can observe this thing. If the same amount of potential difference V volt is applied across these two ends, then the current flowing through this combination, that becomes half. So resultantly, you can write here the resistance of the entire combination, that is equal to 2V upon I. But V by I, that is the resistance of one conductor. So we can write the resistance of the combination, that is equal to 2R. Now see here, in this combination, the cross-sectional area, that is same one, but the length is doubled. So if length is doubled, you are getting the resistance is also doubled. It implies that from this type of experiments, finally you can conclude like this: the resistance of the conductor that directly proportional to length of the conductor. Clear to all of you? Now, let's perform third experiment, in which here take two conductors, both are with length L, but the cross-sectional area, that is A by 2, A by 2. And arrange these two conductors as shown in the figure. Now, here, if the V volt potential difference is applied across these two ends of the conductors, then we can observe this thing, the current flowing through each conductor, that will be equal to I by 2, I by 2. So here current will be distributed. I by 2 from upper one, I by 2 from lower one. Now, here potential difference across each one, that is same one. This is just like the parallel combination. This one, previous one, that is a series combination like that. So here, resistance of each slab that we can write, the potential difference applied, that is V volt, and current through each slab, that is I by 2. So that is 2V by I, but V by I, that is R. So 2R. So here, for each slab, the resistance becomes 2R. See, length of the conductor, that is same one, L, but the cross-sectional area becomes half. When cross-sectional area becomes half, resistance becomes double. So we can say this thing here, the inverse proportionality is there for the resistance with cross-sectional area. So we can write the resistance of the conductor that inversely proportional to the cross-sectional area of the conductor. Clear to all of you? Now, experimentally, we can observe this thing, resistance of the conductor that directly proportional to the length of the conductor, and resistance of the conductor that inversely proportional to the cross-sectional area of the conductor. So collectively, we can write resistance of the conductor that proportional to length upon cross-sectional area. So here, the proportionality constant we introduced, that is rho. So we can write the equation of the resistance R, that is equal to rho L by A, where rho, that is known as the resistivity of the material of conductor. So here we can write rho, that is equal to R A by L. Now unit of resistance R, that is ohm, for area, that is meter square, upon length, for that meter. So meter square upon meter, that is meter. So unit of resistivity, that will be ohm into meter. And now from this particular equation, you can define resistivity also. Suppose we have a conductor having unit cross-sectional area. Then here we have to take A equal to 1 unit. Then per unit length of the conductor, whatever is the resistance, that is called its resistivity. So we can say for the conductor having unit cross-sectional area, the resistance per unit length of the conductor is called the resistivity of the material of the conductor. Clear? Now, Ohm's law in a vector form. Say, as per Ohm's law, we write V equal to IR. But R, that is equal to rho L upon A. So resultantly, we can write V equal to I rho L upon A. Now take this L on left hand side. So we can write V by L. Then on right hand side, we can write I upon A into rho. Now V by L, that is electric field. In previous chapter, we discussed V by D. Here potential difference is applied across two ends of the conductor and length of the conductor is L. So V by L, that is E, electric field developed in the conductor. I upon A. I, that is the current flowing through the cross-sectional area. And this particular current, that is uniformly distributed over that cross-section. So if this current is divided by the cross-section, then we will get the current through unit cross-sectional area. And that is called current density. That is called current density. And it is denoted by J. So we can write E, that is equal to J rho, J, that is current density. It is I upon A. So its unit will be ampere per meter square. Now, make J as a subject of equation. So we can write J, that is 1 upon rho into E. Now reciprocal of resistivity, that is called conductivity, and it is denoted by sigma. It is scalar quantity. Resistivity and conductivity, that is scalar quantity, but electric field and current density, that is vector quantity. So we can rewrite this equation in the vector form as vector J equal to sigma into vector E. So this particular equation itself is called Ohm's law in vector form. Clear to all of you?